Hello, and thank you for joining us today for This is No Ordinary Hard Hat. We'll be speaking with Anupam Sengupta and Flavio Villanustre, and we'll be talking about a case study to improve industrial health and safety outcomes with open source big data. We have two fantastic speakers for you today. We've got, we've moved forward a little bit. We have Flavio Villanustre, who's the VP of Technology for LexisNexis Risk Solutions. He heads up the Hpcc Systems platform, and he'll spend approximately the first 10 minutes going through that option. It is a completely free open source big data platform. Following, Anupam Sengupta, who's the CTO and co-founder of GuardHat, will go through his case study, which is extremely interesting, and I think you'll have a lot of really good information, including real-time IoT. I'm going to go ahead and hand everything over to Flavio, but before we get started, please remember at the bottom of each slide you'll see the Twitter handles for both HPC Systems and GuardHat, and we'd appreciate it if you would include those in any of your social media posts. All right, Flavio, over to you.
Thank you very much, Jessica, and hello everyone, and thank you for being here. I have the pleasure to introduce you to our open source platform, the Hpcc Systems platform, which is a big data platform that we developed originally for LexisNexis Risk Solutions many years ago. This is now close to 17 years ago, and we have been using it for all of our data systems and products, and for our analytical pipeline as well. And since we made it open source, a number of other organizations have taken Hpcc and are using it to drive their own products and systems. And the case of GuardHat is a very good one, so I hope you enjoy this presentation. So just to give you a little bit of a background, as I said before, we started around 2001. We eventually decided to release this as an open source project to power an open source community behind it, just to continue to drive innovation into the platform and to ensure the long-term survivability of this platform. We believe that is the best we can have out there, and we can, with this way, guarantee that the platform will continue to be developed and enhanced over time. And over the last several years, as an open source project, we have been getting a number of other capabilities, not just within the platform, but also outside of the platform to better equip this open source community behind it. And things like online, massive open training systems, those are free online as well in our Hpcc Systems portal, reference there. And we added a number of connectors and capabilities around certainly Internet of Things, which is quite prevalent nowadays, and a number of other systems, integration with other systems that can allow for an easier move of data in and out and an easier use of the platform. And certainly we have improved the support for newer hardware. Nowadays, heavily multi-core parallel hardware is available. So a platform that was originally designed to work distributed across many computers now can also take very advantage of the multiprocessing that is within each one of those computers too. So just to give you a little bit of a background on the problems that we try to solve with this platform, and the core problem is always data integration. Data that comes to the systems are typically data sets that are not completely clean. There are issues with the data, and these issues can have to do with consistency, with integrity, even semantics of the content. But given enough data sources that are partially overlapping, all of these problems can be solved by superimposing these data sources, and this disambiguating the discrepancies by looking at the agreement from the other data sources. So the platform has capabilities around this, in particular for the integration, but of course it has also all of the other orchestration and data workflow capabilities that allow you to even get the data there and process it in an efficient manner. So getting a little bit more towards how you do this, on the top of the screen you will see that any usual big data processing pipeline looks like this. You take data, you integrate that data into a single repository. This is also known as a data lake. You will probably need to profile the data to understand which data elements you have, how the data is structured, which fields you have, how those fields are distributed, what is the content and what values you have, and on and on. You will need to clean the data, and now you will essentially remove all the incorrect values and normalize as well and standardize these values. And eventually, once you go to that point, you can do a analysis. And before you go to the analysis, or as part of that analysis, one of the important components is linking. You will connect the different values in the different data sets to build a consistent view of your data warehouse. And Hpcc particularly excels at this. You can see that little graph in the middle of the funnel. So we've been moving from left to right. Now, right in the middle, just before the little circle, you can see how all the data can be connected. And now different elements from different records in the different data sets can be part of or reference to a single entity if they apply, right, if that's applicable. And of course, on the right-hand side, then you deliver the data. And Hpcc gives you a consistent platform to do this entire data pipeline in just one single homogeneous system. That's quite important because it reduces the difficulties and the complexity to learning and integrating many different little systems to get this type of results. So just going into the platform itself, the platform is, the Hpcc Systems platform is just a software that runs on Linux, and it is more typically deployed in a distributed manner. You might have many computers, and you make all of them work for the same purpose. But it can also be used in a single computer, and we will see that later. So there is no requirement that you would, and no assumption that you would have many computers running at any given time. But if you need more space or more processing power, certainly that is a way to scale. But the most relevant feature that comes for this particular aspect of the platform is the fact that it supports a data flow declarative language called ECL. And you always can wonder why a different language, why not some language that was already there. The reason for the language is that the data problems are better fit by declarative programming models. When you declare things in a programming model, you are telling the system what you want, and the system decides how to do that in an efficient manner. This is exactly how SQL works. The main difference there between ECL and SQL is the fact that ECL also gives you more structured programming abilities. So you can encapsulate your code and your data, you can execute things when they are needed rather than at all times. It allows you to reuse modules, things that are quite attractive when you are dealing with very large data sets, particularly if the data operations that you're doing could potentially force you to go through the data sets more than one time. So the system, the compiler for ECL, which by the way compiles this ECL code automatically into C++ and object code, does all of the optimization behind the scenes to ensure that the code that you wrote runs in the most efficient way. And as I said before, the platform will give you the entire data pipeline. On the left-hand side, your raw data coming into the system, into this data lake. And for that, the platform has one subsystem called Thor. Thor is meant to do data integration and data analysis, batch-oriented data analysis. So you get lots of data, you run a big process to do some massive analytics. This is not very different to what you would do in Hadoop, but without the complexity of coding these things in MapReduce or any of the specific Hadoop languages. And on the right-hand side, you see Roxy. Roxy is the data delivery engine. Roxy is a scalable data delivery engine that has all of the features of a relational database from the standpoint of a programming. So the way you can create store procedures in your SQL code for a relational database, You can do the same thing with ECL. You create what is called ECL queries. And on the front end, it will expose all of these services as web services, such as SOAP or RESTful interfaces, JSON certainly, and ODBC and JDBC in case you would like to have an SQL interface. The interesting aspect of this is that the same ECL language that you use to define those data integration workflows and those analytical pipelines on Thor is used to also create these queries in Roxy. So you can learn one language and you can manage the entire data pipeline. Of course, this platform also has analytic components using machine learning, which will give you the extra capabilities that you typically need without taking your data out of it. As I mentioned before, Thor will do the data integration. It will do this efficiently. It will be coded in ECL. Again, Thor can run in one machine or one virtual machine even, or a large cluster with many machines or many instances in a public cloud environment, which is perfectly fine, right, if you use AWS or Azure or any other public cloud environment. Roxy, the same way, will run in one or more systems. Again, both run on Linux, and both are consistent and have the same type of code base. And it will the same way support cloud environments and physical servers. And last but not least, ECL gives you this declarative approach to data programming. You essentially define what things are. It's the same as in SQL, where you define that you want to get all of the records from a table that match a particular criteria, or you want to do a join across two tables based on a key and then sort the result. Well, all of that can be done in ECL. Each one of these is an ECL primitive. So ECL is a very high-level language, even higher level than SQL. So it allows you to create very concise, very succinct programs that are quite feature-rich, and it has all of the guardrails necessary to ensure that your code is safe as well. So it is less likely to have any defects from a security standpoint, for example, or any other functional defects on the code. Now, the core feature is the fact that it's declarative, so it allows you to say what to do rather than how to do it. As I said before, this platform runs in a single machine, in a single virtual machine, or in a large cluster of machines or instances in a public cloud environment. And just to finish this introduction to HPCC, to get Anupam on the real case study, the number of capabilities that I mentioned are layered across a software stack for HPCC. And this software stack also includes, as I said at the beginning, some integration services with other programming languages. For example, you might be comfortable programming in Python, and you wouldn't want maybe to port your existing code base from Python to ECL, in which case you can embed Python. Or you might be comfortable or may just already have data in a Spark, and you wouldn't like to move your data out of Spark, so you can still integrate the entire HPC stack with Spark. And the same applies to many other languages, including R, Java, JavaScript, and others that are not listed in this slide. So just without more preamble, let's get Anupam to go with his core case analysis for Hvac. Anupam, the floor is yours.
Thank you, Flavio. Thanks for that great introduction. Hi, everyone. Good morning, good afternoon, and good evening, depending on where you are. So I am Anupam Sengupta, CTO at Hvac, and today I'm going to talk about both the Hvac system in general and also the HPCC integration and what we have achieved with it in particular. So moving on to the first slide, you might be wondering, what is Hvac? So a quick introduction about what is this product and what is the solution. We are a Michigan-based startup. We started the company in 2014, and what we are building is a intelligent end-to-end solution, not just a point product, but an end-to-end solution, which deals specifically with industrial safety for workers on the field. So a little bit of background, many of the co-founders, including myself, actually come from the industrial background. We used to run major steel and other metals and mining operations in the US. So one of the core issues we have seen across the board when it comes to worker safety on the fields, especially in heavy industrial areas, but also in utilities and whatever you name, is that many of the injuries that we see on the field in terms of workers getting hurt or unfortunately sometimes fatalities also happens because of two main reasons. One is that incidents as they develop, hazardous conditions as they develop, sometimes the reaction time to actually detect those conditions and take a safety course of action becomes very long. So it's sometimes very too late to react to conditions as they apply, and then obviously an incident happens. And the second thing which we found is that if an incident does happen, the reaction time to mitigate or take action on that incident in order to save lives or take corrective action also is equally long. In essence, the problem is that there is no real-time condition view of what's happening to a worker as they are working on the field or on the workshop or on the floor. And the conditions may include environmental conditions such as emerging hazardous gases, rising temperatures, proximity to live wires. I mean, there are many such conditions that need to be detected. And also the second thing is that there is no real-time control loop back to the safety managers, safety operators who can actually monitor the situation in real time and take action. So from this basic problem statement, we actually formed the product GuardHat. It's a combination of a IoT wearable, that's where the name comes from, GuardHat. It's actually a smart helmet or a smart hard hat, as you would see on workers on the field or on the road, or it's a mandatory piece of equipment in most industries. So we have a front-end device which is a smart helmet which has sensors inbuilt into it in terms of measuring the environment. It has a very high precision location system embedded in it which works both indoors and outdoors. So it's not your vanilla GPS, but much more than that. It has a onboard compute which allows it to operate even in conditions where there is no backhaul connectivity to the servers. And this is where we differ quite significantly from traditional IoT, where we do not assume or presume that there is connectivity always present. We actually have a large degree of autonomy on the device itself. And the device also has a full-fledged push-to-talk plus a inbuilt VoIP telephony communication system, which allows the workers to actually talk to an operator or to anyone else within the closed network at any point of time with the semantics of a usual telephone call, or if they are used to using a CB radio or a LAN mobile radio, they can use the push-to-talk function also. So this is the device. We have accompanying infrastructure which provides the connectivity to the devices as well as assists with the location system, and also does our edge telemetry. So we have edge telemetry built into the solution, which basically means that the processing happens as close to the devices as possible and doesn't necessarily have to make a round trip to a server farm either on the cloud or on the data center. It's possible, but not necessary. And finally, we have our backend IoT platform, which processes the data, and that's where actually Hpcc comes in, which I'll get into a little bit later, where we do the heavy lifting in terms of looking at the aggregate stream of data that's coming in, to processing on it, to condition detection, and also manage the devices. So in essence, if you were to summarize, it's an industrial safety solution with three components: the smart hard hat, which is the wearable IoT device, the infrastructure which comes in between, and the backend software which does the heavy lifting and that also does the analytics. This is actually a platform that we are building, so not just these 3-point devices. There are other solutions and ancillary peripherals which enrich the solution as well in terms of what the worker sees and uses on the field. So moving on, I already addressed some of the safety problems that we are addressing, but these are some numbers which may make the focus a little bit more specific. In the US alone, consistently for the last 4 or 5 years, the number of on-the-job fatalities, unfortunately, has been 4,000 plus every year. It hovers around that number. So if you were to translate it, it's close to 13 deaths every day. Just think about it. 13 industrial deaths every day in the US alone. And that does not even include other injuries which are in the tune of 3 million plus. So that's obviously a situation that's unacceptable. And even though in all developed economies certainly, but across the world, safety is a major objective to achieve in these industries, it's actually very hard to do. The reason is that most of the processes are again tied to the fact that there is no contextual awareness of what's happening in real time. The systems are fragmented, and often it's really based on pen and paper end of the day in terms of assessing the safety situation, making point inspections, and hoping that that works out. That's a problem we are trying to actually solve here. Just to give you a perspective on how the state of the industry has been emerging, and this is specifically with industrial hats, the picture that you see on the left on the slide depicts three helmets in three different categories. The first one, the top one, is motorbike helmets. And as you can see, the evolution over the last 40 years or so has been dramatic. You now have smart helmets which have rear view vision, which talk to you, which have an audio interface, which gives you real-time awareness of vehicles near you, and basically makes your life simpler and safer as you're riding the bike. Similarly, if you look at NFL helmets, they have also evolved quite a bit. I mean, concussion has been a major topic of conversation and concern, and the technology has evolved with it. So you have helmets today which not only let you position the player in real time on the field. In fact, that's how you actually get all those playoff scenarios being drawn in real time as you are watching the Monday Night Football. But they also measure the concussions, the impacts that the players are facing, and let the support staff on the field take corrective action very, very quickly. But unfortunately, if you look at the workers' hard hat, there has not been much innovation over the last 40 years. The materials have become better, they have become lighter, the harnesses have become more comfortable, but the basic premise of the hard hat has remained the same. It basically is a piece of equipment which just exists to protect you from impacts, and that's it. And that's what we're trying to say, change with Guard Hat. Moving to the next slide, I spoke a little bit about the solution. Let's go a little deeper into it. As I said before, it's a three-part solution. The first part is a set of wearables. The hard hat, the smart hard hat, is a key component, but we do have other form factors, including what we call a tag, which does a limited amount of the same functionality. This essentially has a onboard modular sensor package. The sensors can be changed based on the industry in which it is being applied. We have a real-time telemetry happening from the sensors to the backend and also locally. We have real-time location services, that's RTLS, so we can position the worker in real time. And when I say real time, we are talking sub-second, about 500 milliseconds on an average, with the precision of less than a meter in all cases, and in certain ideal cases, less than 40 centimeters or so. So basically, if you're sitting across a table, we can actually tell which side of the table you're placed on. We have audiovisual communication, real-time communication, both in the terms of traditional telephony as well as in terms of push-to-talk, which is more applicable for industrial situations, given the LMR usage there. We have local intelligence built into the wearable so that even if connectivity is not present, we can still detect and act on many of the conditions. And finally, we have the devices also act as a personal area network over various RF mechanisms, radio mechanisms, which allow us to extend the hard hat experience to other connected devices. A simple example could be connecting the hat to a heads-up display or a smart glasses, and then basically evolving the gestalt of the combination of those two devices, or connecting to a smartphone, let's say. So those combinations are definitely possible. The second piece of the solution is the Iot platform, and this is a combination of this platform software and the infrastructure. I'll not go into too much detail except that it is built as a platform, so it is not tied to the specific Guard Hat hardware itself. It can actually connect to other devices also, and this becomes important later on as we look at the analytics and data processing side of things, because often the need is to multi-source data from various different sources, whether it be the Guard Hat product itself or static sensors which already coexist, or external sources such as weather data and what have you, and then meld that data in and process insights and inferences from that mashed up data. So that's where the platform aspect comes in. We do have third-party front ends apart from our own safety solutions, so the data can be fed into downstream systems as well for post-processing. Classic example could be a enterprise-wide data warehouse, but you can obviously consume it in other forms in other systems as well. And finally, we have what we consider HPCC to be in our case, our real-time data analytics engine, but that's actually not doing it justice. It's more than that. We actually consider it to be our data grant station, and people who have been in Chicago probably get that reference. It's a data exchange of how data comes in, how is it processed, routed, cleansed, everything that you can think from a data processing perspective happens there. And what we the end result that we achieve is from a application perspective. Obviously, the first application is our industrial safety solution, but the platform actually is generic enough where it can evolve into various other applications or use cases which would be of use on the field. For example, asset management, time and tracking, path optimization, MRO optimization. So quite a few use cases exist. The first one we are coming into the market with, however, is industrial safety. So moving on, I'll just go through a few of the use cases just to get the system in context a little bit more. So what can the system actually do? There are three use cases I want to just talk through very quickly. We can do what is called a lockout violation detection and also mitigation. This is actually of vital interest in the industries that we are targeting. A lockout is nothing more than a authorized geofence that is established to limit access to certain areas or certain pieces of equipment. For example, let's say the electrical subsystem is getting maintained. You have live wires going out there where the electrical engineers are working on. You do not want anyone other than the electrical maintenance team to be present there. So you want to have a mechanism to limit access. Today it is done with physical locks, actual physical lockout tagout locks, as well as with the yellow tape that you may be used to. And we are trying to change that by making it virtual as well and making it real time. Fall from elevation is a major cause of many of the injuries that our workers face. And we actually have a real-time fall detection system built into the hat, which activates as you're falling. It turns on the camera so that the system now knows where you are, what situation you're facing. It can also turn on the audio system so that you can talk to the worker who has had a fall. And the system can, in fact, notify nearby workers who are wearing similar dart hats to call for assistance right away. And that is, again, based on geolocation. So the nearest worker gets notified first. So we try to accelerate the remediation as fast as possible. The last case that I'll talk about is exposure to toxic gases and toxic environmental conditions. So particulate matter also comes into this. Whereas the trends measured by the system start rising in terms of toxic levels, we can make a early notification to the users to evacuate the area. We can actually do inbuilt mustering within the system also so that we can count who is still in that hazardous area and who is outside. We can automatically geofence that area so that we can restrict the access. And also from an analytics perspective, we can actually measure the trends as they build up over time. So not only is it real time, it actually gives us trends over a period of time so that can be further action through actual maintenance of whatever needs to be fixed. So quite a few other use cases. I mean, we address close to 22 such use cases. I've just given you 3 examples to get us started on this conversation. But we do a lot more in terms of what the system can do. So it's a comprehensive package which essentially gives you real-time position, lets you monitor contexts and situations in real time, lets you action them, lets you communicate to the people who are wearing the hats, and finally gives you a platform which is extensible and you can essentially add peripherals and other devices to enrich the experience. So moving on, this is where we start tying back the conversation into how Hpcc came into the picture. So as Flavio mentioned in his slides, it's really a data pipeline that we are talking about. And the data pipeline concept, especially in this context of IoT, becomes even more important because that's what it is. You're essentially getting a stream of data from the devices on nodes, which is depicted here on the left side. You are doing various processing on it. It's from traditional data cleansing, traditional quote-unquote ETL, transforms, data mashup, refining the data in ASN. doing some pre-processing to do deduplication, probably doing pre-computes if necessary. So a lot of pre-staging activity happens, and then you essentially go into the event processing side, where this is where the IoT flavor really comes in, where you are really dealing with a stream of events that are coming in from various devices in real time. And again, in our case, real time really means sub-second. So it could be 300 milliseconds to 500 milliseconds, where every device is sending a tick and sending a data packet that needs to be processed. So we need to do complex event processing across devices and within a device across the temporal line in real time, and try to infer conditions as they're emerging. So we don't just detect events, we also detect emergent conditions. So that's where the CEP processing happens. Based on what is detected, what the CEP system detects, you can take corrective actions, which can be as simple as just notifying the worker that a condition is happening and they should take mitigative actions, to going all the way and actually shutting off the cause for that conditions. For example, you can actually shut off machinery if that's what is needed to fix the issue. From that point onwards, as you go beyond the real-time perspective, once you have a corpus of data, you obviously want to see trends, derive insights, do analytics, do reports, including regulatory reports that OSHA requires, for example, incident reports or near-miss reports. So that's where, again, Hpcc comes in, where we actually use the same data engine to do our analytics, do our data processing, to generate our reports, both for visualizing within the system as well as propagating or feeding the data downstream into other systems where they can be visualized by other analysts or the consumers. One other interesting concept here is that we do pull in external data where it is required. So it's not just a closed system in terms of only the IoT devices feeding in data. We can actually feed in data from external sources, do the data correlation where it makes sense. For example, a simple situation could be weather data as it's coming in, which is also a real-time source. And they can be blended in or melded in with the IoT data that's coming from the devices. And if microclimate or a weather-centric view of the system can be established, because not every condition applies for every weather condition. So moving on a little bit more. One of the challenges we have here is that the volume of data that we have is extremely large. As you can imagine, if you're doing real-time data sensing, and let's say a site has about anywhere between 500 to 1,000 such devices, and those are just guard hat devices. There are other data sources also. In such a case, the data volume that comes in is extremely, extremely large. Just to give you a sense of it, every day, every work shift, we are generating close to 17 megabytes of just telemetry data. And that does not include media, of course, which takes it by a couple of orders more. And you have multitude of such devices coming in every working shift, which is an 8-hour shift. So that multiplied by 3 times, multiplied by 365, we kind of get the idea that the volume that we are treating is extremely large. The second challenge that we face is that this is a real-time system. So there is really no concept of rolling back or resubmitting a job in case something fails. You have to get it right as the data is coming in. And especially because it's safety-centric, so every second counts. So you cannot really afford to have a pipeline which is suboptimal. So one of the things which we actually also face, apart from this, is that the usage pattern of the system is based on the fact that it is both data aggregation as well as trending of, based on trending of past historical data, which you need to do in real time. So basically, let's say, just to give you an example, gas levels rising tend to rise over a period of time. So it's a trend. So it's not a point in time data, but it's a trend. So at every data check or every event processing step, you're basically not only looking at the data that's just come in, which you're processing or inspecting right now, but you're also looking at historical data to establish the trends or the other correlations that may exist. The other complication which comes in is that apart from the time-based or the temporal-based pivot, we also have a strong tie-in to geospatial pivots or geolocation-based pivots. So you're also looking at the location, which is moving obviously because people are moving around on the field. So that adds another layer of complication. Another situation which we encounter frequently is that apart from the real-time processing needs, we also use it as our analytics platform. So apart from canned visualizations and analytics, we also have ad hoc queries, essentially, quote-unquote queries going on, which basically means that the system has to adapt both to a traditional OLAP kind of transaction handling or transaction volume, but also act as an OLTP at the same time. So it's pretty unique from that perspective. And finally, there is a regulatory need in many of our geographies, from a PII data handling as well as making sure that the data is data access is limited only in certain situations or to certain categories of people. So that also needs to be handled, from basic masking, pseudonymization, etc. These are some of the challenges which we actually are having in the system, and that's where Hpcc actually came in. So at a very high level, tying back to the pipeline view before that I showed you before, this is how the system actually, our GodHat system today uses the Hpcc platform. The only two components I have shown here are Thor and Roxy, but as you probably would have seen from Flavio's slide, there are many other components, mostly management and data delivery in nature, which we certainly use. But from a core component perspective, the way the system works is, when we ingest data, as the telemetry is happening or telematics is happening in certain cases, as the data is coming in, it's fed in real time into Thor. That's the refinery component, as you may remember from the previous slides, where the Thor basically ingests all our high volume data. We have a staging process which essentially does the data refining on the steps of traditional ETL plus some correlation, a little bit of D2, all the pre-processing that's essentially necessary to get it in the right form and format. We also, in fact, put a auditability component into each data event that comes in so that we can trace back and do audits if required. So that also is done here. And then some of our batch processing also happens on the fly. That's obviously scheduled, but can also be run on demand. Where Roxy comes in is that we use Roxy as a real-time data control loop feedback into our own system. So we use Roxy to essentially do the event determination of emerging conditions, especially dealing with trend-based conditions, but also simpler ones such as the threshold min-maxes and things like that, where we use Roxy's data delivery capabilities, especially the web services data delivery capabilities, to trigger conditions which come back into our own Kyra platform. By the way, GodHat's platform is named Kyra, Kyra, where Kyra gets the feedback in real time from Hpcc for any emergent conditions, and then it does the appropriate action. So whether it be delivery of a notification, turning off an equipment, calling up EMS, or whatever else you can think of, it's actually configurable. The sync up with Thor, by the way, is, while it is predominantly real-time because of the need of the system, we do have bulk data feeds also once in a while, which essentially deals with configuration. It deals with bulk data that may be sourced from external systems. And in a few cases, we actually push back audit data also in order to re-audit certain situations. So what do we get out of this? End of the day is, because we have Thor which can handle large volumes of data and can scale to our needs. So we have a deployment models ranging all the way from a simple edge system processing the data for a limited set of hats to all the way going up to multi-cluster data processing based on multiple sites actually feeding in data. So Thor actually scales to all those models. And from a Roxy perspective, the advantage is that it's very flexible in terms of how we as the Kyra platform or the end consumer want to ingest the data. So if it is a low volume data, we can certainly use web services. If it is higher volume data that we need to consume, which we do need in certain cases, especially when we are doing mapping, where you have multiple polygon data coming back, we can use bulk data connectors also. So it's also quite flexible in terms of ingestion. But the biggest flexibility we actually see is that as far as Hpcc is concerned, from our perspective, it's a one-stop solution using a single paradigm of using ECL as a declarative mechanism to state what we need, which ties all these pieces together. So basically, I do not need a separate set of skills to run Thor versus Roxy, even though their usages are very different. I don't have to really spend too much time on setting up the infrastructure, setting up a cluster manager, looking at Zookeeper, looking at data endpoints, working on different languages and different paradigms just to get data moved from point A to point B after a certain processing. So it abstracts away all those complexities for us. In fact, when we started in 2014 and when we started with Hpcc in 2015, one of the striking points of why we ended up with Hpcc is that it was extremely easy for us to stand up the capabilities that we needed with a limited set of resources. And as you can imagine, startups always starved of resources. But we were able to do that very, very quickly. Also, the fact that ECL is actually domain-centric in the sense that it's very data-oriented and it's declarative made the development aspect of what we built much, much simpler. And it scaled along with our solution as we grew the solution itself. So that was another key thing. So in summary, we use Roxy and Thor in a very real-time reactive model. We use both components. The first one is essentially used as our refinery, data refinery, or our staging area, as well as our repository for historical data. It also helps us with the batch analytics. Roxy is our real-time data data feed from Hpcc, and it also helps us detect real-time conditions as they happen. And the two systems obviously talk to each other. So moving on, this is just a view of some of the capabilities we have achieved with the system. So this is the visualization side of things, what the end user ends up seeing. So we have multiple perspectives and multiple views that are derived from our system today. Many of the data elements coming from Hpcc, either post-processed or through Roxy. So for example, we have dynamic dashboards and reports which we can establish, which gives the end user views into what's happening at an aggregate level at their sites across whatever operations they may have. It allows them to drill down into each category or each incident or each location for that matter. And the views update in real time, obviously. It also gives you a KPI view of whatever KPIs may be of interest in terms of number of incidents, number of corrective actions, reaction times, etc. Whatever may be the key performance indicators are also visualized here. We obviously have the core of the system, which is the real-time event detection and visualization, which is the central slide in the middle. This gives you a real-time view, both with a map-based geolocation view, as well as a sensory view and a trend view of what's happening to the workers on the field as things are happening or emerging. You can obviously also start a communication with that worker in real time as well. And what this slide doesn't do justice is that all these views are dynamic. So if it were a real system or a real screen share, you would actually see the values changing in real time as things are changing in the field also. A lot of trend analytics capabilities. We are working towards actually integrating more of ML to derive insights or discover insights and correlations. Now, it's still in the early stages right now, but results are quite encouraging at this point. And again, that's being run out of Hpcc. And finally, what we really achieve in terms of end goals is that we have now real-time analytics and event detection, thanks to Hpcc's integration with Cairo. We have ability to do trending and insights, both using ML as well as traditional analytics mechanisms. We have a large degree of visualization because end of the day, the way you represent the data in the UI is sometimes more important than the data itself, unfortunately or fortunately. So that's also possible. We have the capability to do multi-sourcing, so we are not just tied to our own system in terms of where the data can come from, but we can actually ingest it from various sources and normalize as we go along. Data mashup is a subsequent capability that we gave from multi-sourcing. And finally, equally important is that it's not a closed system. So it's it's a system where we can actually have the data be liberated from the end system. So we can feed the data into downstream systems for other integrations or other data processing in the enterprise. So the data can actually flow out completely of the system as well. So just to summarize a little bit, what did we achieve with Hpcc? What were the value points which we got from Hpcc? So obviously we have enabled our safety solution. That's our product, that's our solution, that's what we are going into the market with, and that's the central part of it. But apart from that, some of the other things we got in dealing with Hpcc is, number one, it's a domain-based solution. I've talked about that before. It's very easy to model and use Hpcc exactly for the application that you have in mind. The rapid development in terms of having to know only one language and also have a batteries included, so to speak, platform, which gives you all the capabilities right out of the box with minimal configuration, was extremely important and beneficial, especially in a startup scenario. Data integrations we have spoken about. Also have scalability in terms of using the system all the way from a simple virtual machine running on a laptop of a developer to running multiple clusters on AWS. So that capability is extremely viable, and we have actually used it to great effect. The deployment model is very flexible, so you can use what you need and scale up as you grow. So the other way to look at it is what you don't know won't hurt you in this case. So you can start small and scale up with your solution. It's also future-proof. It's an open-source product, of course, but in terms of its capabilities also, it's evolving over time. So over the last 2 or 3 years, we have already gone through at least 3 major releases with various different capabilities that are coming in. And I know for a fact that the platform is evolving as we speak, so new capabilities are in the pipeline as well. Incremental build-up we have already spoken about. The last thing which I would want to touch upon is that even though it is open source, the amount of support that we have received over the years from Hpcc systems, Flavio's team as well as the engineering teams, has been phenomenal, both in terms of basic support, so how do I do this, what is this particular issue, how do I get around that, to actually influencing some of the changes that the platform has had in order to meet our needs, which was really, frankly, for an open source platform, has been mind-blowing for us. And that definitely has helped quite a bit in terms of us moving along with our solution. So in summary, from a real-life use case perspective, the system is actually already in the field. Almost all of 2017 was spent by us in field trials with very large customers in real-life situations. I cannot name them, unfortunately, because of NDA reasons, but we have had great success in the oil and gas industry, in metals and mining. We have a system which has been running more than a year right now in the field. In fact, the field trial for 3 months was extended by the customer to be perpetual at this point, or at least there's no end date at this point, so they're extending it right now. So it is actually in the hands of real users. They are using the system, both the hardware and the software, to great effect. Field trials obviously give you an opportunity to get real-life feedback from people who actually are going to use the system, so that has come in. But one of the main key points where people, our end users, were pleasantly wowed by the experience was the real-time aspect and the visualizations. And thanks to Hpcc for making some of those things happen. So this is in real life. We are expanding our pilots. We are expanding our customer engagements. We do anticipate that you'll hear more about us towards later half of this year. So in final assessment, what we have, where I want to end this slide today is that we found Hpcc really, the systems, to be really something that fit our needs almost to the last T. It allowed us to grow with the system over time. It didn't overwhelm us. From a development perspective, we were able to also use our limited resources to great effect. We have actually used it way and beyond what it was originally meant for, and Hpcc was kind enough to make changes to the system to make it happen for us. And from a usage perspective, we do see a long-time viability with this, and thanks to the support of Hpcc, both the community and the company, to make this happen. So I'll actually end here at this point, and we would be open to taking questions. There is a lot more work to be done. I I would not say that we are done with HPCC at this point, but the capabilities what we have found so far has been extremely viable in terms of what we wanted to do. Thank you.
All right, thank you so much, Anupam. So just a reminder to everyone, at the bottom of your screen, you'll see a little question box. We absolutely welcome your questions, and Anupam and Flavio are standing by to answer any questions that you might have. So while Anupam and Flavio review the questions, I'd like to apologize for some of the technical difficulties that we had. For some reason, some of our slides have looked a little odd. I want to invite you to go to the attachments and links, and you can download the presentation there, and you will see all the slides as they were intended to be viewed, and perhaps you can see things a little bit more clearly. All right, so we're going to turn over here to some of the questions. All right, so the first question is, what types of results have you seen from the guard hat implementations?
Thank you, Jessica. I'll probably take that. The results have been overwhelmingly encouraging. Encouraging in terms of acceptance, encouraging in terms of actually achieving the results that we were looking for when we deployed the solution. Without going into too much details, the two key features or factors of guard hat which really enable the solution to look viable to the users is, number one, the real-time aspect of the system. And real-time not only in terms of detecting events as they happen, but also the hidden or the latent aspect of the fact that the system is actually capturing data even in a blue sky situation. So even if things are going well, nothing is going wrong, there's no safety scenario emerging, the system is still collecting data on what's happening on the field. So there are a lot of side benefits or downstream benefits to having access to that data. For example, from simple situations such as planning your maintenance. Let's say you have a gas pipeline and you want to basically look for leaks and basically mitigate them or fix them before they become something else. Having access to data from guard hat has been extremely valuable in determining such situations. And you can obviously extend it or extrapolate it into the other scenarios also. So that's number one. The second biggest factor was that for the first time really in many of this end customer industry, there is now a mechanism to know the location of your worker in real time. It's not necessarily Big Brother, though that aspect does come in, and we do have some mitigations around that. But the fact that you do know who's where to the last second makes both operational and safety aspects of managing that operation much simpler. So overall feedback extremely positive, extremely high amount of acceptance. Of course, we have got feedback on certain changes that we have made, and the field trials were valuable for that. But at this point, let me just put it this way, that we can't make those devices fast enough. Let me put it just in that fashion. Hope that answers that question.
Yeah, that's great news, Anupam. All right, it looks like we have possibly a few other questions coming in. Here's another one, Anupam. What types of conditions does the system measure? Heartbeat, body temperature, or ambient air conditions?
Sure, Jessica. Short answer is all three. Longer answer is the system is actually modular. So we can and do detect biometric conditions. Do not claim to be a FDA-approved clinical device, but we can certainly detect trends, which may be of equal importance. Biometric, however, is a little complicated because there are PII elements to it, privacy elements and regulations, which dictate how much we can collect and how much we can show or visualize. But within those constraints, we can certainly do that. So the technology is there. Ambient conditions, right from ambient air, particulates or gas levels to ambient temperature, humidity. Basically name it. If there is a sensor for it, we can modularize and package it in. We also do quite a bit of contextual condition detections. Apart from location, we can also detect proximity to hazardous devices using various technologies. That's also possible. And in certain cases, even if the sensor is not built into the hat, thanks to the personal area network or the PAN capability, we have the capability to actually read off sensor data from a fixed sensor system also. So let's say there is a fixed sensor mounted on a wall and you happen to be walking past it. If the connectivity is enabled, we can just read out those sensor data right away and then push it out of post-processing. So it's very modular in that fashion.
All right, thank you. All right. Here's another question, and this might be both for Anupam and Flavio. So what were the biggest challenges implementing Cassandra with Hpcc systems?
I don't know, Anupam, if you'd like to address the size of the application on Hpcc and Cassandra, or you'd like me to address the integration itself between Cassandra and Hpcc?
I can probably take the first part very quickly.
Okay, good.
Sure. So from a Cassandra perspective, the Cassandra capability did not exist when we first started. So our first integration with Hpcc was essentially a very unusual mechanism of using Roxy, where we were using not only as the data delivery, we were actually using it in a reverse fashion to push data back into Hpcc. That did work for a while, but Cassandra obviously coming in gave us a much easier and canonical mechanism of synchronizing data between the two systems. So from a Cassandra perspective, the biggest challenge really is, and this is where again I compare it with the Hpcc. In order to have a reliable Cassandra deployment, you have to have a cluster. You have to have a number of nodes. You have to have a controller or a sentinel process. And managing that becomes difficult as you scale up. It's not impossible, but that's where some of the challenges come from. It's a solved problem. There are patterns of doing how you do that. But regardless, that's something you need to go through. Cassandra for us remains just a staging mechanism at this point. So we don't do much with Cassandra other than using it as the data delivery system into Hpcc. But if you do want to use Cassandra beyond that usage, and there are valid use cases for doing so, you obviously will face the challenges in terms of how do you integrate it back into your system, how do you ensure consistency across the cluster, how do you manage the sentinels and things like that. So biggest challenge really was the fact that you need to manage the clusters there. And again, our usage of Cassandra is very simple, so I'm sure there are other challenges that may come up as you use it more, but for us, that's been the core. Over to you, Flavio.
Very good. And on my side, I think there are two pieces to this answer. One is the complexity of integration, and just to answer that piece, it wasn't too complex to get Cassandra to integrate properly with Hpcc. As a matter of fact, we have also integrated Cassandra to support we used to have functionality in Hpcc that was implemented in its own manner around the logical file management, around the work unit management, and we now move some of that functionality as well into Cassandra, if you want to have Cassandra. Otherwise, you can still use the legacy mode there. So it hasn't been too hard, and it has given us a more scalable way to deal with all of these other capabilities. But on the functionality side of adding Cassandra, Anupam just touched on that, and that is extremely important. Roxy was traditionally meant to be a read-only store, so it's great to do data delivery when you want to do complex real-time analytics, for example, or deliver data in very large volumes of data when you have terabytes and terabytes, petabytes of data that you want to deliver in real time in a few 100 milliseconds. But it does not offer the ability to mutate the data. So it doesn't, unlike an OLTP, it doesn't allow you to change the data in real time. And there were ways we managed to do that using other relational databases integrated with Roxy, like MySQL. But it was less scalable than we would want to be, because those databases tend not to be very scalable. Adding Cassandra as a scalable, mutable data store into Roxy means that now we can have both benefits: the large scalability and the large performance of Roxy distributed, and the ability to have mutable data. If we need to change the data in real time, we can do that without needing to go through an expensive process to move the data through Thor to prepare it and then back into Roxy.
All right, thank you. We're almost at the top of the hour, just almost out of time. I'm going to ask one really quick question. How many hats can the system monitor? And what else is GuardHat monitoring in addition to the geolocation? Do the BI dashboards, are they also open source? And so what all is open source from the modules?
Sure. I think it's a two-part question, Jessica, so I'll take the first one. And the dashboard, probably I'll let Flavia talk through that in terms of visualization. From a hats perspective, we can scale quite a bit. Right now, the system is built to handle in the range of 500 to 1,000 hats easily within a single system. And of course, with the horizontal scaling ability, both of the network or the infrastructure components, as well as the backend software, I mean, there is really no limit other than how much compute can you put into that system. The system does partition itself, so it's not that a single point of failure would exist if we were to scale that way. So just from a numbers perspective, if you have to go with a number, I would say anywhere between 500 to 1,000, depending on the configuration that's required there. Apart from geolocation, what we are monitoring is, as I said before, based on the modular sensors, we are monitoring those sensor values. We are monitoring proximity to devices. We have the AV system, which can actually also provide you with a visual monitoring system if you want it. So it's like an industrial GoPro, quote unquote. Think of it that way. That's the easiest way to describe it. We monitor ambient noise levels. So that's another key thing that's actually part of the sensor package. And really the system being modular basically means that if there is a sensor for it, if it's small enough, we can monitor that parameter. So that's not a limitation. From a dashboard perspective, I'll just quickly speak about what we do, and then I'll hand it over to Flavia because there's a lot more visualization in the platform itself. We use our own dashboarding system, and that is partly historical because of the way we built it out. We do have plans to leverage the visualization capabilities of Hpcc systems a lot more, but from our perspective, we have our own inbuilt solution. However, we do have the data feeds which can feed into any BI platform of your choice, so that should not be a limitation. Flavia, over to you.
Yeah, on the dashboard. On the dashboard question, on the piece of visualization, this can be all provided through Hpcc. It has native interfaces to build dashboards through ECL and using Roxy or Thor. The information that you display in a table can also be displayed in a graph, in a graphical manner. It has all web-enabled components that have been also integrated from other open source projects for visualization. So it shouldn't be too hard to create a meaningful dashboard just directly with Hpcc and ECL and pretty much nothing else necessary.
Okay, and we just really quickly, there was another question about the Hpcc platform, and it is completely open source and available for free to the community. Isn't that correct, Flavio?
That is correct. Yeah, all of the components that we describe are open source, are freely available. All the source code is available in GitHub, and as I mentioned before, there is open and free training. There is an open source portal as well for Hpcc with discussions, forums and discussions there, and there are a number of other mechanisms to get other people in the community to help. It's a good, active community, and everyone is pretty much very helpful.